Thank you so much for inviting me today, and welcome everybody. It's a pleasure to be here. Technical problems. Today, welcome to Be Serious, and I will discuss about statistical models and statistical methods, more common statistical methods in healthcare research. The 3 points of today will be to discuss how to interpret a risk, how we present as research descriptive information, and an introduction to statistical models, so which kind of models we use. Let's start to discuss about how to interpret a risk. So one of the questions is, what is a definition of risk? So the risk is referred to potential of a possible loss or harm as a result of some kind of action. So when we discuss about risk in healthcare and the research is more, what is our risk of lung disease or cardiovascular diseases or other diseases that are related to human beings. And one of the questions is, how do we calculate risk? So let's start with an example. We will go through this together. We have 36 individuals that we follow over time for 5 years. And over these 36 individuals, 4 of them will suffer of myocardial infarction within 5 years. So it's 4 individuals over 36. So if we want to calculate what we call in epidemiology absolute risk, and you probably have seen papers and project proposals that discuss about absolute risk, is the number of events that happen, so 4 events, that divided the population at risk at the beginning of the study. So in this example is 36 individuals. And we usually want to show this for 100 people. So if we want to show this for 100 people, it's around 11.1 individuals will develop, over 100 will develop a myocardial infarction in 5 years. And this is an example how we calculate the absolute risk. I have another example. It's about the risk of other conditions like lung cancer, pancreatic cancer, or mesothelioma. And here it's an example of lung cancer of the overall lifetime absolute risk that is around 3%, 2.7%. And this can also be expressed in 1 out of 36 people will be diagnosed with lung cancer at some point in their life. And a little bit lower absolute risk is for pancreatic cancer. In this case, it is 1.6. So that is 1 in 62 people will develop pancreatic cancer. And at the end is an example of a quite rare condition. It's called mesothelioma. It's the cancer that is not related to the lung, but is related to the pleury. That is the cover that we have the membrane around the lung, but you can see that the absolute risk in the population is very, very small. And why I'm discussing about absolute risk? Because the absolute risk is showing us how many people are affected, how much is the burden of this condition in our population. As human beings, we like to compare. All of us like to compare. We compare. It's very difficult for us to discuss about absolute risk. We always compare in life. Also to understand how much time to do something compared to something else. We always compare. I take 10 hours to do this and 5 hours to do something else. So also about the risk in healthcare research, epidemiology, statisticians like to compare. So we use another measure that is not called absolute risk, but we start from absolute risk and we can compare 2 groups. And going back to the example of before, where we were having 36 individuals, in this case, we are among these individuals, we have 17 females and 19 males. So we can compare the risk between the 2 groups. And in this case, we have that among the 17 females, 3 of them develop a myocardial infarction in 5 years, and only 1 male develop the condition within 5 years. And we can calculate the absolute risk in females, as we said before, and absolute risk in males. The absolute risk in females will be the number of events divided the number of female at risk. So as you can see, we have 3 events, 3 myocardial infarction in 5 years, divided the overall number of females. that is 17. So it's around 0.17. And the absolute risk in males is 1 divided 19, because it's one event, divided 19 people, so the absolute risk is 0.05. And how can we compare females and males? To compare females and males, we calculate a measure called risk ratio, that is equal to the absolute risk in the females divided the absolute risk in males. So in this case, it's 0.17 divided 0.05. And it's equal to 3.4. And how we do interpret 3.4? We interpret 3.4 that females have a 3.4 higher risk to develop myocardial infarction than males in this population. So the risk ratio is a way to compare two absolute risk in two groups. You probably have heard already a lot about risk ratio. And here I want to show some example how you can find in papers or in project proposal, they can display the risk ratio. So the risk ratio is a measure to compare the risk between two groups. And here is an example of risk ratio for cardiovascular diseases. And as you can see, there is the comparison between males and females, starting from the left, to smoking versus non-smoking, to eating a diet based on vegetable compared to a diet not based on vegetable, and also the effect of physical exercise. And how do we interpret this graph? You maybe have seen this a lot of time. How do we interpret this? We interpret this on the base of 1. So everything that is above 1 is an increased risk. Everything that is below 1 is a reduced risk. So as you can see, there is the risk of cardiovascular disease in male versus females here is probably 1.23. So there is like 20% higher risk to develop CVD in males versus females. And for smoking versus not smoking, we have 2.5 times higher risk of CVD in smokers compared to non-smokers. It's interesting to see what's happened when we move below 1. So that is, the factor is protective. So those that have like a vegetable based on diet compared to those that not have a vegetable based on diet have probably a 30% less risk to develop CVD, because from 1 we go to probably around 0.7, so we have 30% less risk. Some of you can ask me, this is like the estimate where we calculated. Some of you can ask, what is this gray bar? This is like what we call confidence interval in statistics, that is a quantity of the uncertainty, because we are never sure what is exactly the risk, but we should say that the risk is, the estimate is 2.5, but the range that is probably the parameter have in the population is within a confidence interval. So we have like a range where the true value of the population can be. And this is why we use confidence interval as a measure to quantify uncertainty associated with the estimate. So to summarize about risk ratio, it's a relative measure. You will have see something similar. We discuss about risk ratio in this case, but you can find something similar research that can sometimes call relative risk. That is the comparison about incidence rate being exposed compared to unexposed, or odds ratio, that is a comparison between two odds in subjects that are exposed and not exposed, and hazard ratio that has a very similar interpretation that is used more in survival models. And I always want to remember that the interpretation of the risk ratio needs to be done also in relation to the absolute risk. And this is why, let me try to explain this. As you can see, here I'm comparing this group compared to this group. Okay, and in this case, we have risk ratio of 3. So think this ball here on the left is the absolute risk, and I'm comparing with the absolute risk in the other group. And the risk ratio is 3. The risk ratio is 3, also in this population, where this is the absolute risk in people exposed, and this is the absolute risk in the people unexposed. What I'm trying to say, that you can find similar risk ratio in population with very different absolute risk. So in this case, the absolute risk is quite high, and this is quite low. So it's always important to interpret in which population we are looking into, to understand how much the risk is really affecting the population. So in some way, a risk ratio 3 in a population where already the risk is quite high, also in those unexposed, is in some way more important than what I can see maybe in this group. In this case, where in both of them the absolute risk is quite is lower than the other population. And this was the first part of what I was trying to discuss with you today, and now I will move on how we present the descriptive information and which kind of information you can find in tables of project proposal, findings, and how we can interpret them. Here it's an example about how we used to present estimates from on categorical variable. So this is a categorical variable, is an ethnic group, and this we have like group that are Asian or Asian British, Black British, or Caribbean African, mixed or multiple ethnic groups, white and other ethnic group. And you can see how we present these estimates, showing the absolute numbers and also the percentage. So how many people in the population that I'm looking into are in each of these categories. And this is how we are presenting variables that are categorical. You can see in this case is an example of ethnic groups. We have used this also for different kind of other categorical variable. It can be like the education level of people, if people maybe have a disease or not, or been vaccinated or not. So are variable that can be categorical, or dichotomous, that maybe have only 2 values. For example, I'm vaccinated, yes or no. And for continuous variable, it's a little bit different. Continuous variable are a variable like BMI, level of cholesterol, and we use the arithmetic mean. That is a way of a central variable, the central value of a set of number, and we can calculate the arithmetic mean for the age, for income, or for different kind of continuous variable. Another value of central value is the median. The median. So the median is the central tendency, and how do we calculate the median is that we put all the numbers that we have for that specific variable in order. For example, this is the number in order, and which we choose the central value. So, and in this case, the central values is the middle number is 9, as you can see. So 1, 2, 3, 4, 5, 6, 7. So I choose the central value, and in this case, the median is 9. And here are a couple of examples where you can see the difference between the mean and the median. So this is like the temperature, the human body temperature of a group of people. Then you probably know that this is like distributed as a normal distribution, more or less, where these 2 values of central tendency are very close to each other. So the mean is 98.63 and the median is 98.65. So they are very close to each other. There are other cases where the mean and the median are not so close. This is the household income distribution in a population in 10,000, more than 10,000 pounds. As you can see, it's not as the distribution as before. There is more or less the majority is in this group, and after we have like the value decrease in this direction. And here the mean and the median are different. As you can see, the mean is bigger than the median. What is the problem of the mean? The problem of the mean that is very susceptible to the extreme. So when you have this kind of extreme here, outlier, we call outlier, or these outliers, so extreme value, they weight in the mean, so they can move the mean, they can move the mean towards one of the tails. So in that case, when you have a distribution that is not normally distributed, as in this case, we prefer use as a value of central tendency the median instead of the mean. And why I'm telling you this? Because healthcare researcher, they know this, and we know that we need to use the median in this case, but we often use the mean because it's easier, because it's what we usually do. But in this example, as a descriptive information for like to describe this variable, is much better to use the median compared to the mean, because the mean is influenced by these values that are more extreme. So please remember this when you review results or project proposal on the use of the median and the mean. And now I would like to give you a very brief introduction about to how we use statistical models. And please interrupt me at any time, because this I want to that you follow this, and to give you a short introduction about this. So let's start from an example. How we have two continuous variables. So we have age, and we want to see how much with age we are increasing the level of systolic blood pressure. So we know that with aging, we have an increase of systolic blood pressure. I also used to have a very, very low systolic blood pressure, and I'm realizing with time, yeah, it's still very low, but it's going up a little bit. And this is probably the process of aging on this. So how can we study this? Yeah, here is an example. Let's start to explain what is this and how we interpret this. So here is the age over time. So we have people that are 20, 30, 40, 50, 60, 70, 80. So this is like our age, and this is our x-axis. And here it's the systolic blood pressure of people, and this is our y-axis. So, and we have one individual, for example, here that is probably 18 years old, and has a systolic blood pressure of, that you see here, is probably 133. So each of these cross is one individual with a specific age and their systolic blood pressure. As you can see, all of these are individuals. When we use a linear regression model, what do we do? When we use a linear regression model, we try to define the line of best fit to show the trend of increasing blood pressure with age. So we have this model called linear regression model, where we can try to estimate the best line that show the average increasing of blood pressure with age. And how do we estimate this? We estimate this using a model we call linear regression model that try to minimize the distance between the line and each of these cross. So when you find the line, it's used like a specific algorithm. We try to find the line, we minimize the distance between each of these point and the line. So in this case, this this line that is this gray line is called residual, so it's the distance of each point to the line. So we try to find the line where the sum of all these residual is the minimum. So we try to minimize the distance between the points, the data points, and the line. And what do I do when I get the line? Yeah, when I get the line, I can calculate the beta coefficient that is showing us that for each unit increase in age, how much does increase the blood pressure. So in this case, this line is telling us that for each unit increase in a year of age, I have a 0.596 increase unit in blood pressure. And this among brackets, you can see it's called constant interval. So it's an interval of confidence where I think the range of this increase can be, as I said, is like give us a level of uncertainty where in the true population the values can be. So this was, let's say, a summary of what is linear regression, where we are using two continuous variables. In this case, we have age, and we have systolic blood pressure, and we try to estimate how much for an increase year of age, how much does increase in average the systolic blood pressure, and this is what we can estimate from the model. And the model is based on maximizing the distance between each point and the line, so to find the minimum distance between each point and the line, and this distance between each point and the line is called residual. And I only show some residual, but each point of each cross have residuals with the line. So this was our overview about linear regression, and I am now happy to discuss with you what I show about risk, about descriptive statistics, and about linear regression, and I also have some additional slides if we want to discuss more about this. Before to finalize, I really want to thank you all of you for your work. I really like to discuss always like with panels of the public about our protocols, our research ideas, the results. So I really thank you for all your work. It's amazing that there's the possibility to work with you and how you contribute to our research. So thank you very much.